So the purpose of L'Hopital's rule is nothing more than being able to find limits resulting in indeterminate form. Now, from Calc 1, you may remember that indeterminate form was 0 over 0. It just meant that when I plugged in, or when I applied direct substitution to some function, I got a form that didn't seem to make sense. It didn't mean that it didn't exist. It was just that, for instance, 0 over 0 doesn't make sense, because not only is it undefined, but if the numerator is 0, then maybe it's 0. So it turned out that there were typically common factors, so that there was no way for us to really interpret it or determine what it was until we did a little algebra. Well, there's lots of indeterminate forms, it turns out. In addition to 0 over 0, we have indeterminate forms when we have infinity over infinity. So for a very similar reason, I want you to realize that, is infinity over infinity infinity? Or is it 1? Maybe because the infinities cancel. Right?
No.
So the point is, who knows, right? You can't determine it from now. What is 0 times anything?
0.
0, good. So what's 0 times infinity?
0.
No, it's indeterminate form. We can't really tell for sure what's happening. Turns out that when you're multiplying 0 times infinity, that's another type of indeterminate form. How about this? What is 5 minus 5?
0.
Good. What's infinity minus infinity then?
Indeterminate.
Okay, again, it's not 0 because these may not be the same sizes of infinity. They may not be the same degree of infinity. And so infinity really turns out to be a peculiar idea now in calculus 2, okay? Because infinity in this case, let's say that I were to look at e to the power of infinity, okay? Multiply e by itself, or 2 to the power of infinity. Multiply 2 by itself an infinite number of times. It would get massively exponentially large. But if you look at 2 times infinity, that's still big, but it didn't quite get as big as 2 to the infinity as quickly. So these could still be different infinities, and so that right there is an indeterminate form as well. There are a couple other indeterminate forms that are powers. What's 1 to any power?
1.
1. So what's 1 to the power of infinity?
Indeterminate form.
Indeterminate form. We again have no idea. Same idea. If I were to take anything to the 0 power is 1. Unless it's infinity to the 0 power, then it's not 1. Or it might be 1. It's indeterminate form. Okay. Another one is going to be 0 to the power of 0. 0 to any power is 0. But then again, anything to the power of 0 is 1. So we're getting conflicting ideas here. So it turns out that all of these are going to be done using a particular technique. Both of these are already in the form to use L'Hopital's rule, because in order to apply L'Hopital's rule, the function has to be a fraction, okay? These in the middle can always be turned into a fraction in order to apply L'Hopital's rule. So tell me, what's L'Hopital's rule say?
Divide every individual term by the highest, or divide every individual term by the highest power of x so that you no longer get those infinity over infinities.
You are right. That was the method we took. That was definitely the method we took in order to eliminate 0 over 0. But that's not what L'Hopital's rule says to do. We actually could evaluate the limit a little different. So somebody tell me what L'Hopital's rule says.
Is it if f of x over g of x is either 0 over 0 or infinity, it's equal to f prime of x over g prime of x?
That's right. It turns out that when we take the limit as x approaches infinity of f of x over g of x, assuming we get zero indeterminate form. If we don't get indeterminate form, L'Hopital's rule will not work, as you maybe saw on Professor Leonard's video yesterday as well, where you get so basically it has to be indeterminate form. But if it is, then L'Hopital's rule says something really, really cool. It says that this is equal to the limit as x approaches infinity of the ratio of their derivatives. That's pretty crazy. But it shouldn't be too surprising overall, because really if I'm taking the limit as x approaches infinity of f divided by g, I'm basically saying how quickly does f increase in comparison to g? Does f increase faster? If it does, then it's going to go to infinity. What if g increases faster? Then it's going to go to 0. What if they both increase at similar rates? Then it might increase to a particular constant. So that must imply that this should be the same value by taking the limit of their rates of change. So this is a really cool process for L'Hopital's rule. So we're just going to start off and do a couple examples now and see how crazy simple this is. Okay, so let's do an example. All right, so let's take the, and I misspoke here, by the way. This does not have to be infinity. The point is that this could be anything. Let me just put c. The limit as x approaches c. It could be anything we want. If you ever get indeterminate form, then this rule applies. Okay, that's what we're saying. So let's take the limit as x approaches, limit as x approaches 0 of sine x minus x over x squared. So this is the limit, as you should notice that if you apply direct substitution here, yields, well, 0 minus 0 over 0, which is 0 over 0. So because it's 0 over 0, in Calc 1, we would have maybe factored the top and bottom and canceled a common factor. Unfortunately, we can't do that here because there's a sine x there. And sometimes we multiply by a conjugate, but that's not going to do us any good because I'm still going to have the sine x. So this is the benefit of using L'Hopital's rule, but it's really important when you use L'Hopital's rule to say that you're using L'Hopital's rule. So what this tells us is that this limit should be exactly the same as the limit as x approaches 0 of the derivative of the top over the derivative of the bottom. We're not applying the quotient rule, mind you. All we're doing is taking the derivative of the top, which is cosine x minus 1, and dividing by the derivative of the bottom, which is 2x. So notice the limit is really important to still be there. You have to put that limit. If you don't put the limit, then this isn't true. We're not saying that this function is equal to this function. We're saying that their limits happen to be the same, so this is a way to find the limits. But this is still not okay. You need to verify or demonstrate that when you go from one step to the next, I want you to write LH for L'Hopital's rule. I have just applied L'Hopital's rule. Okay? All right, well, now we go ahead and calculate again. So if we calculate again, we get cosine of 0, which is 1, minus 1 over 0. Ah, bummer. It's still indeterminate form. Well, that's okay. It just means to do this again. Okay, so we're going to do it again. We're going to apply L'Hopital's rule for a second time. So I'm about to say that that's what I'm doing. I'm applying L'Hopital's rule again. And now we just calculate the limit again. The limit as x approaches 0. Only now I'm taking the second derivative of the original function. But that should make sense why we can do this multiple times, because this is now just a new function of x, and this is now a new function of x. So by taking the derivative of each of the top and bottom, which just happens to be the second derivative of the top and bottom here, it should still give me the same result. Okay, so let's take the derivative again. So the derivative of cosine x is negative sine x. The derivative of -1 is 0. And the derivative of 2x is 2. Well, now let's plug it in. Okay, we end up getting on top 0 over 2. But notice that that's no longer indeterminate form. So we're done. This limit is 0. So this limit right up here is equal to 0, even though we originally got indeterminate form. I don't know about you, but that's pretty damn cool. Questions there? All right, cool. Well, I don't want to focus too much on the ones that are already fractions because they're really simple. So I'm going to go ahead and go to another one here. Let's say we want to find the limit as x approaches 0 from the right of x ln x. Now, why do you think it would have this symbol of 0 from the right? Why not just say the limit as x approaches 0? Why do you think we have to have the limit as x approaches 0 from the right to be able to compute this limit?
Absolute value.
Well, there is no absolute value here. Okay, so I'm wondering why do you think that we have to have the limit as x approaches 0 from the right?
Because of the way the graph is made, you can only do it from that side.
Yeah, because look at ln x. Isn't ln x going to look like this? Ln of x is only defined on the right side. So there is no graph over on the left, so I can't take the limit as x approaches 0 from just in general. So I have to look at ln of x as just from the right side in the first place. Okay. Well, let's use L'Hopital's rule. So what do we do?
Convert it into a fraction.
Yeah, the problem is that I can't use L'Hopital's rule because it's not a fraction. So I just have to force this thing to be a fraction by doing one of two things. It doesn't matter which one we do. Okay. We could do the limit as x approaches 0 from the right. And I could keep ln of x as the numerator and then divide by something that's going to give me x ln x, which is really just the reciprocal of the other function. Now let's just verify that sure enough, that gets us right back to the original function. However, I could have done it another way. I could have just said the limit as x approaches 0 from the right, and I could have kept x as the top function and then put ln of x on the bottom. There's no right or wrong way to do it. However, sometimes you'll notice by trying it in one, oh, that was wrong. It's not just ln x because that wouldn't be the same thing. It would be 1 over ln x. So it doesn't matter which one you choose to turn it into, but sometimes you'll notice that one is easier to deal with than the other. So in this case right here, what's easier to differentiate? 1 over x or 1 over ln of x?
1 over x.
Definitely. You can already see that this one right here is a little harder, so that's why I'm not going to do that one. All right, so this is where I'm now going to demonstrate that I'm using L'Hopital's rule. So, well, let's not just demonstrate that yet. Okay, what we should realize here is what happens when we plug in 0. Okay, well, when I plug in 0, that doesn't even make sense. I can't plug in 0 to ln of x. But what is ln of x on the right side of 0?
1?
Not 1.
No.
Just on the right side of 0, as I'm approaching 0 from the right side, what does ln of x become?
Negative infinity.
Yeah, maybe you need to take a look at Desmos here. So let's take a look at ln of x, right? So what we should realize about ln of x is that on the right side of 0, right over here, notice that the graph approaches negative infinity. So notice that this is going to become negative infinity on top. What about 1 over 0 from the right? What about 1 over 0? 1 over 0 is undefined, but what is the limit as x approaches 0 from the right of 1 over x become?
Infinity.
So you got to start realizing that any constant over 0 is not just undefined, it's either infinity or negative infinity. So you got to realize that a over 0 is not just undefined. The quantity of a over 0 is approaching an asymptote. So it's either going way up or way down, right? So if you take a look at 1 over x, right? Let's look at 1 over x then. Right? 1 over x is positive for positive x values. So you should know that that's the graph. So as you look at x equals 0 from the right side, notice that it shoots up to infinity. Okay. Well, that must mean that this one right here is going to be negative infinity over infinity, which is indeterminate form. That's why we're allowed to use L'Hopital's rule in the first place. So we're going to demonstrate that we're about to use L'Hopital's rule. All right, well, that just means differentiate, and we get the limit as x approaches 0 from the right of, well, ln of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. Okay. Any questions there? So we just differentiated the top and bottom. But notice here that if you take a look again, from the right side of here, when I plug in 0 for 1 over x, I get infinity. When I go from 0 from the right of this function on the bottom, I get negative infinity. It's still indeterminate form. So L'Hopital's rule? No? Nobody? Seems an easier way to
Simplify.
simplify the function, right? So how about just say the limit as x approaches 0 from the right, and now multiply by the reciprocal. So I get 1 over x times x squared over negative 1, which means that really what we're doing is calculating the limit as x approaches 0, and notice that one of the x's cancels. So all we're left with is negative x. Well, the limit as x approaches 0 from the left and right of negative x is going to be 0, so this limit is in fact 0. And there's our answer. So what we're demonstrating here is even if the function doesn't look like a fraction, just make it a fraction. And then you can apply L'Hopital's rule to calculate that limit. Cool. All right. Well, let's do another type of indeterminate form, right? One more indeterminate form would be something like the limit as x approaches 0 from the right of 1 over x squared minus cotangent x. Okay. Well, again, the problem with this is that if I plug in 0 to the denominator for the first fraction, notice that that's going to give me infinity minus. And then if you think about the graph of cotangent x has asymptotes of 0 and pi. And so the limit as x approaches 0 from the right side is also going to be infinity. It's another type of indeterminate form. It's now infinity minus infinity. So I'd like you to take a look at what's going on here on Desmos. if you look at 1 over x squared, on the right side, you can see that it's shooting up to infinity. If you look at cotangent x, you can see, sure enough, on the right side, it's also shooting up to infinity. And what we're trying to do is find what's the limit as x approaches infinity, x approaches 0 of 1 over x squared minus cotangent x. And so I can already see from the graph that it appears that the answer is also going to be infinity. But don't let that fool you. Just because you've got infinity minus infinity doesn't mean your answer is going to automatically be infinity. Just like this one up here, I took the limit and it turned out to be an answer of 0. So the key here is to try to get this to be a single fraction here. Okay. So there's a couple of ways to do this. Perhaps you could just get a common denominator for cotangent x. Perhaps you thought to rewrite this as limit as x approaches 0 from the right of 1 over x squared minus 1 over tangent x. Right? Or maybe you chose to rewrite it as that we kind of have an option about how we want to handle this. If we want to get this to be a common denominator of x squared over here by just multiplying top and bottom by x squared, we could do that. If we choose to turn cotangent x into 1 over tangent x, we could do that. If we choose to change cotangent x into cosine x over sine x, we could do that. There's lots of ways to handle this. I don't really care how you do it. I'm going to change to sines and cosines because they're easier to differentiate. So that's just my choice. And at that point, we need to get it to become a single fraction. Okay. So if I do that, I'm just going to multiply each fraction by the other denominator. So this will become sine x minus x squared cosine x. And the bottom is just going to be our common denominator of x squared sine x. Everybody cool with that? So we just have to, if we're expected to calculate this limit of an indeterminate form, our goal is to just turn into a fraction somehow. Okay. But notice that this just gave us a different type of indeterminate form. Okay. Because if you plug in 0 for each of those quantities there, notice that you get 0 for sine of x, you get 0 times cosine x, and then on the bottom you get 0 as well. So all that happened is that this just became a different type of indeterminate form. But because it's a fraction, I know that I'm going to be able to apply L'Hopital's rule. Cool. All right, well, let's keep going with that then. So L'Hopital's rule just says differentiate the top and bottom, right? So we get the limit as x approaches 0 from the right. And now we're differentiating each of these. But be careful, because notice that x squared cosine x and x squared sine x, those are both products. So we're going to have to make sure that we apply the rule on each of these functions when we differentiate. Okay. So the derivative of sine x is cosine x and minus, and now we take the product rule. Okay. It gives us the first times the derivative of the second plus the second times the derivative of the first. And on the bottom, that's going to become, again, same idea. So it's the first, which is x squared, times the derivative of the second, plus the second times the derivative of the first. Now, again, every step along the way, you've got to check to make sure that you get some particular, some particular quantity here. if you keep getting indeterminate form, then you keep doing L'Hopital's rule. But don't just keep differentiating top and bottom if you end up getting some answer, because your limit will not be the same. So we try this again. So we get the limit as x approaches 0 from the right of cosine x. Well, that's 1. Minus, well, the limit as x approaches 0 of this next term is just 0. And the limit of this last term is also 0. So we're left with 1 minus 0 plus 0 over. And now we take the limit of each of the terms on the bottom and we get 0 plus 0, which gives me 1 over 0. All right. Well, now we just do L'Hopital's rule again, right? You can stop me whenever you want here. No. Okay, I'll stop myself then. No, we can't use L'Hopital's rules. So why can't we use L'Hopital's rule anymore? This was the whole point of it. Why can't we use L'Hopital's rule?
Because now it's undefined instead of indeterminate.
Yeah, this is no longer indeterminate form, right? This right here is an actual answer. That's not indeterminate form. It's not infinity over infinity, and it's not 0 over 0. So this answer is infinity. And that is the limit. As we should have known anyway if we ended up looking at Desmos, right? Desmos ends up showing us that this graph goes off to infinity, okay? So we've dealt with all of these different examples of indeterminate forms. I want you to, I'll go back and kind of highlight what we did. We did an indeterminate form of infinity minus infinity. We did an indeterminate form of, shame on me, I didn't show this one. This right here is going to be 0 times infinity, right? So that was an indeterminate form of 0 times infinity. Okay. This one up here, we had an indeterminate form of 0 over 0. We see down here, there was another, when we switched, we got an indeterminate form of infinity over infinity. So we're dealing with all kinds of different indeterminate forms here. We just want to be able to know how to handle each of those. Okay. Well, the last indeterminate form is anytime you're taking a limit of a function here that becomes basically with a function that's an exponent, where you end up getting an indeterminate form of one of these original ones. So anytime you end up getting one of these indeterminate forms way up here, right, the ones with where you get a power, that's because the function that you were finding the limit of is f of x to the power of g of x. So that's the only way that you're going to be able to get infinities and bases and exponents. So we need to know how to deal with these types of functions. So how about we just take a brief look at limits of f of x to the power of g of x. Okay. There are a couple of ways to approach this. The easiest way to approach this is, well, it doesn't really matter. We'll do both. So one way to do this is to rewrite this as y equals f of x to the power of g of x. So one way to deal with a limit that involves a power to a power, or I'm sorry, a function to a power of a function, is to label it as y equals. And then from there, you can just take the natural log of both sides. And now notice that you have the natural log of y is equal to g of x times the natural log of f of x. by our property of logarithms that allows us to bring that power out of the power. So now notice that we might actually have a product at this point, but notice that that could be a product of like 0 to 0 times infinity or something. So that might still be an issue, because if you had infinity to the power of 0, and then you took the natural log of that, now I'd have 0 times the natural log of infinity, which is 0 times infinity. Still indeterminate form. Or if I had 0 to the power of 0, now I have 0 times the natural log of 0, which if it was from the right side would be 0 times infinity, or negative infinity, which is still indeterminate form. Or if I had 1 to the power of infinity, when I took the natural log of both sides and brought that infinity to the front, now I get infinity times ln1, which is infinity times 0, still indeterminate form. So the point of why these particular indeterminate forms here are special is because when you apply taking the logarithm of both sides, when you move it to the front, you end up still getting a different indeterminate form, but at least now it's a product. And we know how to deal with products. And so that's going to be a bit easier to deal with. But we're still not quite done, because remember, the whole point of this was we're trying to take the limit of both sides. So if I'm trying to take the limit of, if I'm trying to take the limit of f of x to the power of g of x, then that would mean that I'd have to recognize that I'm taking the limit of the left. And so the limit as x approaches c of ln of y. But I'm also taking the limit as x approaches c of this new function where I move g of x to the front. Okay. But keep in mind that what I'm still trying to do is get this y by itself, because y is the original function. The orange thing up here is the original function. So what I'm trying to do here is to now get this by itself, so I can now simplify this a little bit by recognizing that the limit of a log is the log of the limit. And over here, that means that I can just rewrite this and get the limit. I can write this as the limit as x approaches c of g of x times the natural log of f of x. Lastly, remember, y is f of x to the power of g of x. I'm trying to find the limit of f of x to the power of g of x. So all that means is I'm trying to find the limit of y. So the way I can do that is take e to the power of the left and e to the power of the right. And therefore, I have now solved for what the answer is. I can say that this limit, the limit as x approaches c, of f of x to the power of g of x is the same as e to the power of the limit of this function. But this is not something to memorize. Instead, I'm going to show you a slightly easier way to do this. And that's to realize that if I were to bring this back up again, this is nothing more than just e to the power of the natural log of the limit as x approaches c of f of x to the power of g of x. So the way that we're going to handle these, the easiest way I've found anyway, is to simply rewrite this limit. See this limit on the inside here? We're going to rewrite this limit as saying e to the power of ln of the limit, because e to the power of ln cancels. But it's going to allow me to bring this g of x to the front, and then we're going to be able to go from there. Okay, so let's look at this in practice, because this is going to be a little bit easier to deal with, I think, if we end up just looking at an example. So why don't we do this one? Okay, why don't we take the limit as x approaches 0 from the right. Oh no, we're going to do limit as x approaches infinity. So the limit as x approaches infinity of x to the power of 1 over x. So let's just look at this this problem. If I plug in infinity to the base, I get infinity. Looks like I got a couple of questions up here. Sorry for not noticing that earlier. Okay, so let's go back a little bit. Eric said, how would we know that the last problem was equal to infinity and not undefined without using Desmos? Because, as I mentioned earlier, anything over 0 is infinity or negative infinity. So we don't normally say anymore that this is equal to undefined. Okay, so we don't really say that anymore. Now we're recognizing that any constant over 0 is going to be infinity or negative infinity. But really, I mean, it's going to be negative infinity only if a happens to be negative. It'll be infinity otherwise. Okay, so that's kind of how we knew that. The next question, we know that a constant over 0 equals either infinity or negative infinity. So Dion, thank you for answering that earlier. Eric, I got to tell you, when I'm doing the work on OneNote here, I don't have the chat open, so it's just sometimes when I see it blinking up there that I recognize I got to go back to that. How do you know if it's positive or negative? So Sophie said you could draw a graph and plug in points to figure out which direction the infinity is going. In general, the other reason is whether or not the constant is negative or positive. Okay. And that's about it. So everybody clear on that now? Did I answer your questions? And thank you, Dion and Sophie, for helping out as well. Okay, so anybody else have questions before we kind of continue on with this one? Okay, so getting back to the problem here, if I were to plug in infinity to x, I get infinity, and if I plug in infinity to x here, I get 1 over infinity. What's 1 over infinity?
0.
That will be a really important fact as we move forward into chapter 5, that if you take 1 over a massively infinite number, your answer is approaching 0. So this gives us an indeterminate form of infinity to the power of 0. So here's what we're going to do instead. Okay, we're going to rewrite this function. We're going to rewrite this limit by saying the limit as x approaches infinity of, and now we're going to rewrite this as e to the power of ln of x to the 1 over x. So hopefully you see that this is the exact same function as the original function, because e to the ln of u is u. So this is just another way for us to write this, but there's a reason why I would do this, because notice that since the exponent has a logarithm, that's going to allow me to move that 1 over x out to the front. So this is going to be the limit as x approaches infinity of e to the power of 1 over x times ln of x. Everybody okay with that so far? All right, well, now notice that because I'm taking the limit of an exponential function by our exponential rule for limits, what this is always going to allow me to do is just rewrite this as e to the power of the limit as x approaches infinity of, and I'm just going to rewrite 1 over x times ln x as ln of x over x. So at this point right here, this is where you're now just going to start using L'Hopital's rule in the numerator. So the purpose, anytime you have an indeterminate form with an exponent like this, that just means that you're going to apply this process to be able to get the numerator to be a quotient so that I can use L'Hopital's rule. Okay? So we're going to apply L'Hopital's rule here, but we're going to apply it on the numerator. So we're going to apply L'Hopital's rule. All right, so let's do that. All right, so that's going to become e to the power of the limit as x approaches infinity. Oh, does everybody see why this I could use L'Hopital's rule? Natural log of infinity is right back here. The natural log of infinity is infinity over infinity, and infinity over infinity is sure enough indeterminate form. So basically what this is e to the power of infinity over infinity. So that's not going to work. So what we do instead is we're going to take the derivative here, which gives you ln of x as a derivative of 1 over x over the derivative of x, which is 1. All right, well, that's just equal to e to the limit as x approaches infinity of 1 over x. But what is that limit going to be? What's the limit as x approaches infinity of 1 over x?
1 over infinity.
1 over infinity, which is 0. So isn't that just going to give us e to the power of 0? Which is no longer indeterminate form. The answer is 1. So I'd like to take a look back again at what the point of this was, or what we just did. We were trying to find this limit. And what we've just done is we've said that if you were to look at the graph of this function, x to the power of 1 over x, as you approach infinity, my limit will approach an asymptote of y equals 1. But the way we were able to do that was by rewriting this as e to the power of the natural log of that function, which allowed me to get that power of 1 over x out of the power. And then we can apply L'Hopital's rule, and that's our answer. So you're basically going to be taking e to the power of whatever the limit of this natural logarithm is up top. Okay, so this right here, just this step, this is the key step in dealing with the indeterminate forms that are powers. Okay, I would like to take a look at this graph. And it was x to the power of 1 over x. Okay. Well, if you take a look at this function, you can see that it appears that it increases for a little bit, and then it comes up over 1, and it gets up to, I don't know, about 1.4 or so, a little bit above. But then as you continue to go out to infinity, it appears that this keeps leveling off somewhere. So when you look at this graph as x approaches infinity, let's just realize that those y values seem to keep getting closer and closer to some value. I don't know, I can't tell. Let's zoom out a lot more here. Okay, I'd say that's far enough. Let's see where this is getting close to, and I'm all just over at 400. 1.015, looks like it's 1.013. It's still too much. So let's go out to 2000. 1.004. See what's going on here, guys? The whole point of this is that once we see once we take a look at the graph, you can actually see why the limit of this function does in fact become 1. Okay. And that's it. Anybody got any questions on any of this?
I got kind of lost. How did you take e in front of a limit?
Yeah. Okay. So let me put it this way. It's going back to our properties of limits. So if I were to have, let's say I take the limit as x approaches 2 of, well, e to the x. How would you calculate this?
Plug in 2.
You would plug in 2, but aren't you plugging in 2 to the exponent? So the e really is just staying where it is. So doesn't that mean that what I'm really doing is taking the limit of the exponent?
Oh, okay.
So really what we're saying here is if I take the limit of an exponential function, you could just take e to the power of the limit. And that's what we were doing way back here, is that when we took the limit as x approaches, hold on one sec. When I took that, that just means that I can really bring the limit into the exponent, which really meant that now, now I'm able to just use L'Hopital's rule on just the exponent.